Hi everybody, good to have you on this session. My name is Julian, I'm a tech evangelist with AWS, focusing on artificial intelligence and machine learning. In this session, I'm going to show you how to use a deep learning library called Keras, and how to combine it with Apache MXNet, another open source library, and how to run everything on Amazon SageMaker, our managed service for machine learning. Okay, so we'll start with a very quick intro to Keras and MXNet, just to tell you a little bit more about those two libraries, and then we'll see how to run a basic example with Keras, how to train a basic neural network with Keras, and then we'll move on to modifying this Keras script to run it on SageMaker, and we'll see how we can use MXNet as a backend as well. Okay, so lots of stuff to cover, and of course you can ask all your questions on the Twitch channel. We'll take a look periodically at those questions. I'll try to answer as many as I can, and I've got a bunch of friendly people also helping me answering those questions, so thanks to them. Okay, and all questions welcome, so fire away. So let's get started. So I guess the first thing we should talk about is Keras. As you probably know, we have quite a bunch of libraries to choose from now when it comes to building deep learning applications. TensorFlow, Keras, Apache MXNet, PyTorch, Chainer, and more. And specifically, I wanted to talk about Keras today because it is a developer's favorite, I have to say. And as of today, there is no built-in support for Keras in Amazon SageMaker. So I felt, well, this was a good idea to show all the Keras users out there how they can integrate their favorite library on SageMaker. So Keras is an open source project started by François Chollet. So kudos to him. It grew really, really popular. And in a nutshell, Keras is a high-level API that lets you easily build and train all kinds of neural networks, all kinds of different architectures, and then train those models, train those networks using different backends. And initially, Keras supported TensorFlow and Theano. Okay, another popular library for deep learning. And with the release of Keras 2, Keras version 2, Apache MXNet is now supported. Okay, so we'll talk about that in a second. But basically, if you're new to Keras, I would recommend going to the Keras website. There are some pretty good tutorials out there. And again, it's probably the one of the easiest ways to get started with deep learning. So it might take you a little more than 30 seconds, but yeah, the good thing, what I like about Keras is thanks to the high-level API, you don't write a lot of code. It's Python. It's quite easy to write and understand, and the fact that it's high-level helps you build or reuse models with very little code. And so you can focus not on actually writing the code, but you can focus on solving the problem. And as you can see here, there's all kinds of layers, all kinds of network architectures that are supported. So if you want to build convolution layers, you will find those available in Keras. And I have to say, the online documentation for Keras is very, very good. So this is really a good place to start. I can also recommend looking at the blog. Oh, okay, that's not it. Keras.io. Okay, and you'll find lots of tutorials out there. And again, this is a really, really valuable resource. Very high quality examples and showing you how to perform a number of tasks with Keras. Okay, so a good resource to get started with deep learning. So let's look at an example. So to keep things pretty simple, we're going to work with a dataset that I'm sure you've heard about and probably used called MNIST. And MNIST is a collection of 60,000 handwritten digits from 0 to 9, 10 classes, okay? So 60,000 for training and 10,000 for validation. And of course, the name of the game here is to learn how to classify those 10 classes correctly, right? Recognizes that this picture is a 0 or a 5 or a 7, etc. with the right level of accuracy. So let's face it, this isn't really good for anything except learning and experimenting and testing. And the fact that it is a pretty small data set also helps with the training time, so you can quickly try different things. So these are, as you can see, black and white images, 28 by 28 pixels. So it's a really tiny data set, and that's why it's a good pick. So this is actually the first example we're going to look at. So here we're going to train a simple convolution neural network on MNIST, okay, trying to classify those 10 categories correctly. So I'm actually using SageMaker right now. This is a notebook instance, and just to give you a quick look here at the SageMaker console, this is it. You can easily create a notebook instance by clicking on that fancy orange button here, filling in a few pieces of information, and off you go, right? You wait for a few minutes for that instance to come up, and then you can just open it. And when you open it, you actually dive in directly into Jupyter, right? Which is the preferred tool for machine learning engineers and data scientists these days. And that's why they're called notebook instances. So it's an easy way to create your dev and test environment with a fully managed instance running in AWS, and you don't have to mess with anything, right? TensorFlow is pre-installed, Keras is pre-installed, MXNet is pre-installed, Jupyter obviously. So pretty cool way to get started quickly. But of course, if you run Jupyter on your own machine, on your laptop, that works too. This is really vanilla Jupyter here. Okay, so let's look at this example. So I'm importing a few things, and let's run those cells as we go. I'm using the MXNet backend, but we'll get to that later. Okay, it doesn't really matter. This code would run exactly the same if we used TensorFlow. Let's check the Keras version here, 2.16, not the latest, but good enough for our purpose. We're going to use a batch size of 128. We have 10 classes. We're going to train for 10 epochs, and the images, like I said before, are 28 by 28. Okay, so pretty straightforward there. MNIST is a very well-known data set, and most deep learning libraries have utility functions to load or download and load the MNIST data set. So that's the case here for Keras. It's one of those data set APIs here. So we can just load it, and automatically we're going to get the training set, the test set, and each of them comes with the samples, the X matrix, and the labels. Okay, so the ground truth, the actual labels for each of those pictures, and that's the Y vector. Okay. Let's ignore this bit for now. I'll get back to that. This is due to the fact that we are either using MXNet or TensorFlow. Let's get back to that later. So then I'm just going to normalize my data set. Basically, this data set contains pixel values, right? And I'm just going to normalize them between 0 and 1. Again, remember, these are black and white pictures, so the pixel values are from 0 to 255. So normalizing them to values between 0 and 1. And then printing the shape, and then using this utility function to actually encode the labels to bit vectors. Okay, this is a technical one-hot encoding, and if you already do machine learning, you may know that we don't really like to work with categorical variables. So here the labels for the samples are integer values, right, 0 to 9. Okay, and we don't specifically like to do that. We'd rather do one-hot encoding. And let's maybe look at an example here. So if we had a label that says 2, we would actually convert this to, and we have 10 categories, so we'd build a vector of 10 bits. Okay, so that's 6, 7, 8, 9, 10, right? Okay, 4, yep. And this is category 2, so we would flip bit 2 to 1. So bit 0, bit 1, bit 2, okay? So this is called one-hot encoding, okay? And this is how you typically deal with categorical variables in machine learning and of course in deep learning as well. So this function is going to do just that, okay? It's going to take all of the labels for all of the pictures and transform the actual integer value into a bit vector where the corresponding bit is flipped, okay? So this is how we work with categories. Okay, so we do this for the training set and for the test set. All right, so let's run this cell. Okay, so in your case, it would download MNIST from the web. Of course, I've done this before, and I can see the shape, okay, of X-train. So 60,000 samples, 28 by 28 pixels. And just one channel because these are black and white images. If I had red, green, and blue images, if I had color images, I would have red, green, blue channels. So I would have 3 channels. Okay. So actually, my X-train data structure is a 4-dimension array. Okay, and it's called. If you want to be fancy, you're gonna call this a tensor. But if you learned how to code in the previous century like I did, you just call this a multi-dimensional array, right? Same thing. And we get 60,000 samples for training and 10,000 samples for testing. Okay, so there we go. Our data set is ready. Then we can build our simple convolution network. And I'm not going to go into the theory of convolutional networks, but basically here I've got a first convolution layer with 32 filters, and during the training process we will learn the actual values that are stored in those filters, and as you can see there are 3 by 3 filters. So for each filter I need to learn 9 parameters, and that will show me how to extract the right features from those images. Okay, and I'm using the ReLU activation function. Then I have another convolution layer with 64 filters. So convoluting again the pictures that came out of the first layer. And then I'm using pooling. Pooling is an operation that shrinks pictures, just keeping the brightest pixels, so to speak, and throwing away everything else. And then I use dropout, which is a way to randomly set connections to 0, and this actually helps with generalization. Okay, dropout is a technique that fights overfitting, which is a problem that happens very quickly with deep learning. And overfitting means you learn the training set so well that you can't generalize to anything else. So dropout is a good thing to have. And then I can flatten all those tiny images that come out of the pooling layer and classify them using a fully connected layer with 128 neurons. Then adding more dropout, and then actually outputting the probabilities for the 10 classes in that layer. Okay, and don't worry if you're not familiar with those operations, the convolution, the pooling, the dropout, etc., and the dense layers. You will find again lots of information in the Keras documentation, and I will share some resources at the end that give you kind of an introduction to what deep learning is and what convolution is. So for now, let's just accept that this works and that it's going to successfully classify, and then you can dig into the theory later on. Okay, and then finally I compile my model. I pick an optimization function, and I define a metric, which is of course accuracy. Okay, all right, and then I can train. Okay, so I call the fit API, passing my training set, the batch size, the number of epochs, the validation set, etc. Okay, and let's train. Okay, so this is training on my notebook instance. Okay, and this one has a GPU, so it's reasonably fast. If you try this on your laptop or on a non-GPU machine, of course it's going to be quite slower. Okay, so it takes about maybe 10 or 12 seconds per epoch. So we can wait and just go all the way. Let's take a look at questions for a second. Okay. All right. So. Okay, not too many questions now. All right, that's fine. They will come later. All right, I should mute this. Yes. Okay. All right. So we see. What do we see here? We see the training process ongoing pretty much, and we see the accuracy here, right, going up. And this typically gets to 99% plus. Okay, so the way this works is we train on the 60,000 samples, and then we use the validation dataset, the 10,000 samples, to measure accuracy. Okay, and we see here the training accuracy for the last batch, and we see the validation accuracy here, which is those 10,000 samples being predicted and at the end of each epoch. And this goes up again. Yep. So there you go, 99.03. And let's see if we can go up a little more. .1 maybe. Come on. Oh, come on, no, we went down a bit. Okay, so the best epoch was actually this one. So this, if we wanted to predict with this model, this is the one we would keep, right? The one with the highest validation accuracy. Okay, so as you can see, and again, don't worry if you're not super familiar with I would say the theory of deep learning. The important things here are it's Python code. It's not a lot of code, right? And you can really easily build in just a few lines of code. You can build a convolutional neural network. It would be the same for other network architectures, and you can quickly train within minutes by using, like I said, high-level APIs and not worrying about the internals, the low-level stuff that's happening during the training process. Okay, so this is Keras, all right. And I mentioned Keras can use different backends. So I guess we could find something in documentation, right? Oh, come on, this is disappointing. Oh yeah, backend. All right. So we can actually use multiple backends. So like I said, Keras is a high-level API that plugs into a lower-level library. Such as TensorFlow, Theano, and MXNet, even though it's not mentioned here. So, quick word about MXNet. It's part of the Apache incubator. You'll find lots of information on that website and tutorials, etc. And you could use MXNet standalone, right? Just like you could use, of course, TensorFlow standalone. But developers find, again, the Keras API to be friendly, and especially for beginners, it's a good way to get started. So you could have the best of both worlds. You could use the high-level, easy-to-learn Keras API, and you could plug a very fast, very optimized backend like MXNet. MXNet is natively written in C++, and it's quite fast. And I won't go into the discussion of why we would like to use MXNet versus TensorFlow. Run your own benchmarks. I run mine, and well, I'd rather use MXNet. So there's your answer. Okay, benchmarks are a touchy topic, and they're not my topic today. MXNet is scalable. It will support multi-GPU training. It will support multi-instance training, distributed training, etc. So it's probably a good choice for a Keras backend. Okay, and again, you can learn a whole lot more about MXNet, and please feel free to try MXNet standalone as well, just to get a feel for it. So if we want to use Keras with a different backend, actually we have to change the config file, and of course I closed that window. So let's reopen the window. So I'm just gonna get to my terminal here. So this is a terminal on my notebook instance, and this would work the same on your own machine, right? And you have this file called keras.json. Okay, that takes a few parameters, and one of them is called backend. And by default, it's going to say TensorFlow, right? And if you change that to MXNet, and of course you have MXNet installed on your machine, then you're going to start using MXNet, okay? As a matter of fact, there's an extra setting you should use, coming back to that part I didn't explain before. Where is that window? Okay. So when we train here, it complained about this. So the problem here is different libraries are optimized for different data shapes. So we saw the shape of the data here was 60,000 samples, 28 by 20 images, one channel. Okay, so TensorFlow will require that channel number to be last. And actually, MXNet works faster if you put that channel first. Okay, and that's what it says. For performance improvement, please change to channel first format. And this is what we should do here. Okay, so we can do it right away. And just get a little more performance. And of course, it's not going to make a big difference. It's not going to make a big difference for a tiny data set like this one. And so it should say channels first. So that's the explanation for that, that weird message. Okay. So this should be fine. Let's quickly try again. So hopefully this is gone. Okay, see that message is gone. And well, if we train again, okay, it's hard for me to say that it's really faster. But if you had a bigger data set, you would see difference. And again, the only thing that it changes is that it's going to load the data with the channels first. Okay, so the shape of the data that gets loaded on the GPU is actually 1 by 60,000 by 28 by 28. Okay, took me a while to figure this message out, but okay, now we know. All right, so here we go. Now we're using MXNet with Keras in the in an optimized way. So the next step would be, let's say we train here on the notebook instance, and again we could have trained locally on the laptop on any machine, right? This is not taking anything into account, any infrastructure into account. Now what if we need to train on SageMaker? Okay, let's say we have a big data set, we need to scale our training process. We can't just train on a local machine, and we don't want to manage the infrastructure, and we want to rely on the SageMaker managed infrastructure to do this. Okay, so let's take a look. Right. So like I said, there is as of today there is no built-in support for Keras in SageMaker. You can bring your TensorFlow script into an existing TensorFlow environment. You can bring your MXNet code, you can bring PyTorch, you can bring Chainer code directly on SageMaker and run it there. But when it comes to Keras, it's not available yet. So fortunately, SageMaker provides a way for developers to literally run anything. And that means building a custom container, a Docker container, that you will push to AWS and that you will run with SageMaker. Okay, in case you didn't know, all the training and all the prediction activity in SageMaker is taking place with Docker containers. So when you use built-in algos or when you use built-in environments for TensorFlow and MXNet, etc., you actually use containers that AWS built and pushed for you, right? But like I said, you have the option to build your own container, and this is what I want to show you right now. Okay, so let's see how we can do this. And if you're not familiar with Docker, don't run away. There's nothing complicated here. I would suggest going to docker.com and running the tutorial over there. It's going to take you an hour, maybe less, and you will know more than enough to understand everything here. So I will explain what we're doing with Docker, but don't let Docker stop you if you're not familiar with it. Okay. All right. So let's get started. So let's import a few things, and let's look at Dockerfile. So when you build a Docker container, you need a file called a Dockerfile that will list all the actions that are required to build a container. Okay. So here for fun and for a little more than fun actually, I decided to write two Docker files. One for CPU-based training and one for GPU-based training, okay? And you could argue that, well, I guess the GPU version knows how to train on CPU as well. So why do you make us look at two files here? There's one good reason. As you will see, the GPU container needs to store, of course, all the CUDA environment, right? All the NVIDIA libraries that are required to drive the GPUs. And these are a little heavy. So the CPU-based container ends up being 1.1 gigabyte or something. And the GPU container ends up being maybe 2.5 gigabytes. Okay, so there's a bit of a GPU tax to pay here. So if you don't need that, if you're not training on GPU machines, then it's really a waste of network bandwidth and storage, I guess, to carry around those bigger containers. So and then it will show you two examples instead of one, which is good, I guess. Okay, so let's look at the Dockerfile for CPU. So this from directive tells me which image I should start from. Okay, when you build a container, you don't start from scratch, even though you could, right? But here I want to start from Ubuntu 16, and I'm going to run these package commands to install some dependencies for MXNet and make sure I got the latest Python environment as well. Okay, just updating everything. I'm going to copy my script, so my Keras script, into the container. Okay, and this is important because it needs to be in that special place. It needs to be called /opt/program/train. This is actually the script that SageMaker will invoke. It's the entry point, if you will. Okay, so we need to make it executable as well. Okay, so the very few things that you need to learn and maybe adapt to when you move existing deep learning code to SageMaker is all related to they're all related to interfacing SageMaker with that code. Okay, and this is one example of that. Then I'm going to copy my configuration file, okay, because I want to use MXNet, so it's the exact same file that you saw before. Copy it into the container. Then I'm going to install MXNet, okay, and I'm going to install Keras MXNet, which is the version of Keras that supports MXNet as a backend. Then I clean up a few things, and that's it. Okay, so like I said, if you don't know Docker, you can follow along, right? You can understand what this does. So again, don't let Docker stop you. It is very easy to build those images and bring them to SageMaker and run everything there. Okay, let's look at the GPU version. It's almost the same. I will just highlight the differences. So this time I'm starting from a CUDA 9 image from NVIDIA, and this gives me all the CUDA libraries and the NVIDIA drivers, etc. And this can be a little tricky to install, so it's good to start from this image and avoid any issue. Everything else is the same except this, right? Installing the version of MXNet that has CUDA 9 support. Okay, that is actually linked against those CUDA libraries, and the rest is the same. Okay, so as you can see, you don't need to be a Docker expert to do this. I'm not one, and I pulled through. So if I did it, anyone can. All right. So I'm going to copy those files to a local directory to build my container. I'm going to copy my Keras script and my config file to this directory called build, and I can see this stuff here, right? So this is local on my notebook instance. Okay, my Docker files, my config file, my script, and we'll look at that one later because it has a few changes compared to the version you saw before. Okay, and now I should be ready to build, right? So because this notebook will let you build the CPU version and the GPU version, I need to define some variables. We can let's build the GPU version, okay? Those settings are pretty much the same. So I need to define a repository name in ECR. So ECR is the Docker repository in AWS, and this is where we're going to push that Docker container. SageMaker needs the containers to be in ECR to be able to grab them, okay? So that's the name. That's the tag I will apply on the container. Okay, just a name that I define, and this is just another name for the training job that I'm going to run on SageMaker. Okay, just makes it easier to find those in the SageMaker console, and we'll see them here, I guess, right when we start training. Okay, I'm going to train on a P38XL instance. That's a big one. It's completely unneeded for a small data set like this, but like I say all the time, I'm not paying my AWS bills, so hey, let's have fun. I'm going to use 2 GPUs from that instance, okay? And the batch size will be 256. All right, so just some constants I'm defining, and I'm also making them available as environment variables so that I can refer to them in my script below. Okay. Now, the next step is to make sure I have an ECR repository. And of course, I have one already. I just quickly show you ECR. Okay, so private Docker repository service in AWS. So I've got a repo already here. Okay, and this is where I will push my image, right? So if it didn't exist, it would have been created using the AWS command line, and then I log into that repository. Okay, and from now on, the rest is standard Docker stuff. So let's build the image. So I call Docker build using the Dockerfile that I showed you, and with the tag that I defined. Okay, and as you can see, it's going to run all those instructions from the Dockerfile. Okay, so updating packages, copying my script, blah 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 blah. Okay, and here it's quite fast because it's cached. I already did this on the instance. So if you do this for the first time, it's going to download packages from the web. It's going to take a little longer, but okay, there's no point in wasting minutes to look at this. And then my image has been tagged, okay, and okay, now tagged it with the repository name. And I can see if I call that Docker images command, I will see this image that I created on my laptop, okay? And again, it's cached, so it's a little older, but you would see the same result. And as you can see, it is 3 gigabytes large compared to the CPU version, which is 1.4. So you could say, well, okay, who cares? It's not so much about storage. It's really about the size of the containers that get deployed to SageMaker. Why for SageMaker to bring 3 gigabytes worth of container to an instance if you only need 1.4? Your training jobs will just start faster if you have smaller containers. So that's a good reason to have the smallest containers. Okay, and now I can push it, right? So again, this is instant. This takes place instantly because the image didn't change, and it's already been pushed to the ECR repository. If you run this for the first time, it will push the layers, and it takes a couple of minutes to push this to ECR. Okay, but that's the process. All right, so now we have a custom container. It's been pushed to ECR, and we're ready to train with it. Okay, and from now on, I would say we're back into SageMaker world. There's nothing specific from now on. We're going to train with the SageMaker SDK in exactly the same fashion as we would with built-in containers. Okay, so again, like you see, as you can see here, the only specific part is building the container, making sure the entry point for the container is well defined, pushing that to ECR, okay, and then you can just use that container on SageMaker, just like everything else. So what should we do now? So we should upload our amnesty dataset to S3, okay? Because that's where SageMaker will grab data from. It needs to be in S3, okay? So I need to put this in the training set in the right place and the test set in the right place, okay? Now, of course, I need to run that cell, otherwise we'll have problems. Okay. And we have a bucket that will be used to save the train model. And training, like I said, now is completely standard. We just use the SageMaker SDK. We use this estimator object, which is the generic training object in SageMaker. And it requires a few parameters. So the image name, so that's really the name of the container that we created, okay? And yeah, that name here, right? The base name, so that's just the text string that I defined earlier to visualize my jobs in the console. I'm going to pick one instance of the type that I defined earlier, so that's a P3 8XL. And the output path is where SageMaker is going to write the train model, okay? And again, this is really no different from what you would do with built-in containers. Then I would need to set some hyperparameters. So these are parameters that will be passed to my Keras script. And of course, as you can guess, this does require a bit of code into the script. We'll look at those while the training runs. And so I'm passing a learning rate, the number of epochs, the number of GPUs. You'll see why. It's not strictly a hyperparameter, but that's a convenient way to pass it here, and the batch size, okay? And then I'm training. So let's get started. Okay, and so what's going to happen now is standard SageMaker stuff. SageMaker creates that P3 8XL instance. It's going to pull the container that I created to that instance, and it's going to invoke that train script that I copied into the container with those parameters and the location of my dataset. Okay, and once this starts within a few minutes, we'll see the Keras training log and we'll get the train model at the end. All right. So let's while this starts, we need to look at the Keras script, okay? Because as I said before a few times, we need to do a few modifications, and those mostly are related to, they're exclusively related actually, to interfacing that code with SageMaker. So let's take a look. Oh, where is, okay, here it is. Okay, so just to be clear, this is the exact same example that we trained before on the notebook instance initially, with a few modifications to run it on SageMaker. So I guess you can guess what I had to change. It's all about interfacing. So the interface between SageMaker and this code is, I would say, the input interface is passing hyperparameters, passing the location of the training set, okay? And the output interface is saving the model, okay? And that's about it. So nothing scary, nothing scary. And this is how we do it. So you'll find in the documentation that SageMaker provides all the input information in well-known locations, right? Thank God, no surprises. So you will find the hyperparameters inside the container at /opt/ml /input/config /hyperparameters.json. Okay, so those hyperparameters here, right, they end up being written by SageMaker into a JSON file inside the container, right? Simple enough. So of course, I need to read those hyperparameters and apply them to my code, okay? So that's pretty much it for hyperparameters. The location of the data will be also passed in there. Okay, so no worries. So of course I had to change this because I couldn't. If you look at that initial script, okay, I used this utility function in Keras to load MNIST, right, in a very lazy and friendly way. So that was great. Of course, here I want to really do it in the SageMaker way. So I'm loading the files from S3. Okay, yes, I could have been lazy again and used that API, but I would have downloaded the dataset from the internet. And that's not really what I want to do. What I want to do is pretend this is a real live dataset and load it from S3. Okay, so I just took that loading function and hacked it to load from the container, right? Anyway, you wouldn't have to do this with a real data set. It's just that because I needed to replace that utility function. Okay, so let's move on to the main code. So as we just said, we need to load the hyperparameters. So it's pretty easy. I just need to open that file /opt/ blah 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 blah, right? And read the learning rate, the batch size, the epochs, and the GPU count. And I provide default values just in case I forgot to pass something to my script. Okay. I can read the input data config. Actually, I'm not using it here with this basic example, but if you wanted to, here the data set is really small, so it's going to be replicated to all instances that train on it. So I'm just using one instance anyway, but if I wanted to do distributed training here, it would be replicated. If you have a larger data set, you probably don't want to do this, and SageMaker will let you shard the data set across instances using a certain key, etc. And this is what you would get in that input data config parameters. Okay, but okay, I don't want to dive too deep on SageMaker here. All right, and now that we have our hyperparameters, as you can see, everything else here, right, is exactly the same. And this is that channel order thing, again, that we saw previously. So just reading from the config file, basically, if I'm using MXNet, I need to have channels first, so I need to reshape my data. If I have TensorFlow, I need to have the channels at the end, and so I need to make sure that's where they are. Okay. Normalizing, converting, building the model, all that stuff is identical, and which is great because it means the bulk of your Keras code will not have to change when you port it, when you adapt it for SageMaker. You will just have to adapt the interface, but the actual Keras code itself stays the same. The one cool thing here is this version of Keras supports MXNet as a backend, and as I've said before, MXNet makes it very easy to use multiple GPUs to train. Okay, with other libraries, you may have to do this manually, split the data across GPUs, but nothing like this with MXNet. So in this version of Keras, there's an extra MXNet specific API called MultiGPU model that lets you say, hey, you know what, the model that we just created here, let's just run it on multiple GPUs, okay? And this is one of the hyperparameters that I passed, okay? And that's all it takes to distribute the training job over multiple GPUs in the same instance, okay? The rest is the same, okay? And then once I'm done training, of course, I want to save the model because maybe I want to grab it from S3 and deploy it on my machine or test it or whatever you guys want to do with it. Or I could go on and deploy it on SageMaker and deploy it to SageMaker managed infrastructure. Okay, so I need to make sure it's saved in S3 in the path that has been defined up there. And again, since I'm using MXNet, I can actually save a Keras model in a HD5 format. So that's the native Keras format. But as I used MXNet as a backend, I can also save this as an MXNet model. So now I would have the opportunity either to use the Keras model in Keras, or I could use the MXNet model in MXNet. Even though I trained it with Keras, I could now take it and predict with MXNet only, not using Keras, and probably getting even better performance. So like I said, you get the best of both worlds. You get the easy, flexible API in Keras, but you can still grab an MXNet model at the end and predict maybe with a native C++ API in MXNet to get the fastest prediction possible, not going through the Python layers of Keras. Okay, and that's it. Okay, so again, just modifying that script for the input, which pretty much means hyperparameters and data configuration, and modifying the script for output, just saving the models. So let's go back to our training instance here. So what do we see now? We see, okay, we're using MXNet, that's good news. These are the hyperparameters that have been passed, okay, which match the ones that have been passed here, so good news. The input parameters, that's the input data config I mentioned earlier. So like I said, data is fully replicated, so SageMaker grabs the full data set and copies it to each of the training instances. That doesn't matter here because it's a single instance and it's a small data set anyway. If you had 100 terabytes of data, you wouldn't want to do that. You would want to do distributed training and shard the data across different instances. And you'll see how to do this in the SageMaker doc. Okay, I see the shape, and then I see my training log, right? And well, there's a lot of surprise here, right? The first epoch takes 12 seconds, and well, the last one takes 2, right? So there's a bit of initialization happening here, but pretty much all the other epochs take 2 seconds. Okay, so you see the boost that we get on that previous training. I was training on a P2 instance, right? So one P2 GPU. It's the K80 from NVIDIA, previous generation, and it took 12 or 15 seconds, whatever it was, with that GPU. Let's 11 seconds. And now if I use 2 of those newer GPUs in the P3 family, and these are the V100s, the latest GPU chips, then it takes 2 seconds. So training is 6 times faster, even on a very small data set like this. So imagine what you can get with a real-life data sets. The P3 family is blazingly fast. Okay, and we get to the end of our training. We get accuracy of 99.15, which is a little better than before. I'm not sure why, but I'll take that. And we save our models to /opt/blah, blah, blah. Okay, whatever locations SageMaker is expecting the models to be saved at. Okay, it took about 2 minutes to run all of this, and then of course SageMaker will grab the models here. The content of that file, of that directory, is transformed into a gzip tar file, and that's copied to S3. Okay, so if we take a look in the S3 bucket, we should see, okay, so that's, yeah, looks like that time. Okay, yep, July 19, 12:23, that's about right. I can grab this. Okay, and I should be able to look at it. Yep, that looks correct. All right, and this is what we expect. Okay, we see the HD5 model in the Keras format. So again, now on my local machine, I could load this and work with it. And I see my MXNet model, and MXNet models come in 2 files. The parameters, right? And let's extract this. The parameters, and this is a binary file storing the weights. Okay, that we learned during training, and of course we have a JSON file which stores the definition of that model. Okay, and so we see exactly the model that we created, the convolutional layers, the 32 filters in the first layer, etc., etc. Okay, so no big surprise, and again we could use that JSON file to load the model from the parameters and work with it in MXNet. Okay, so we went all the way there. So we'll take a look at questions in a minute, but in a nutshell, this is how you would use Keras on SageMaker. Okay, and as you can see, it is as easy as adding a few lines of code to read hyperparameters, a few lines of code to save your model in the right place, put everything in a custom container, CPU-based, GPU-based, and again, don't let Docker scare you if you don't know Docker. Run the tutorial on docker.com and you will know more than enough to write those files. I showed you how to use a different backend for Keras, so it's very easy to use MXNet, which tends to run faster than other libraries and brings you a multi-GPU support in Keras very easily as well. And yeah, I guess that's it. That's what we saw today. And you could reuse the same technique to run everything else. I wrote a similar example for PyTorch, but whatever library you use, and even if it's not a Python library, it could be a C++ library, it could be your own custom code. This exact same technique, building a container, reading parameters, etc., would work the same. So you can use this as hopefully as a blueprint to customize your own examples. So before we look at questions, I want to point out a few resources that you might find useful. So if you're curious about SageMaker, of course, you should go and read about it on the web. You'll find documentation and plenty of good stuff in there. And we announced a whole bunch of new SageMaker features at the New York Summit just days ago. Batch prediction and some new built-in algos. So it keeps moving pretty fast. So you might need to read the doc for that. The GitHub repo for the SageMaker examples is a great collection of notebooks that show you how to use the built-in algos, how to use TensorFlow, MXNet, PyTorch, etc. on SageMaker. This keeps growing as well. So if you haven't checked it out lately, you should. Surely there will be new examples here. The SageMaker SDK is on GitHub as well, so the one that you use to create the training jobs, the prediction jobs, etc. If you use Spark, there's a Spark SDK as well, so you can fire up training jobs or prediction jobs in SageMaker from Spark, from your EMR cluster or your Spark cluster if you run on premise. Okay, so that's really good. It's really an interesting topic that would be worthy of another session. How to mix Spark and SageMaker. And if you want to stay in touch, I'd be more than happy to share content with you on Twitter. And again, if you have cool projects involving SageMaker, Keras, and whatnot, feel free to ping me on Twitter. I'm more than happy to retweet and share all your good stuff. My blog on Medium, and actually this example that we saw today comes from one of my blog posts, and yeah, like I said, there's another one for PyTorch as well. Okay, so keep an eye out for more blog posts as soon as I have some time to write them. And I've got also a growing collection of videos on YouTube from AWS summits and third-party conferences, etc. And if you're specifically interested in the theory of deep learning, there's a session there. It's in the Dev Days playlist where you'll learn about fully connected networks and convolution networks, and I go a little deeper, quite deeper into the theory that I've done today. Well, plenty of good videos to learn about SageMaker, etc. And the code that I use today is on my GitLab repo, DR notebooks, and you'll find notebooks for SageMaker and Spark and Keras, and again, more stuff coming as soon as I have time to write it. So there you go, plenty of stuff to read. Let's take a look. We have a few more minutes. So let's see. Let's see if we have questions. Okay, let's grab. So I'll grab the last few questions. Okay, but feel free to ask your questions again if you're up the list. So you don't know. You don't need to change the Keras code for CPU and GPU. Basically, that's why I passed this hyperparameter, the GPU count parameter. If I wanted to train on CPU, I would just say 0, right? I would say 0 GPUs need to be used, and then that multi-GPU model function that I used here, right, would not be used. Okay, so it's a bit of a hack, but I like it. So this gives me the same script for CPU and GPU, and thanks to that GPU count hyperparameter. Okay, but yeah, the rest of the code is exactly the same, which is very convenient, I think. So next question: any timeline on when the Keras containers will be provided out of the box? I don't know, is the honest answer. So in the Keras, in the TensorFlow container, oh wow, this gets recursive now. In the TensorFlow container, you can use the tf.keras layers. Okay, so it's not quite the same as using Keras directly, but within TensorFlow you could use the Keras layers to build a model, and then use the rest of the Keras, the rest of the TensorFlow APIs. So that's possible now with the built-in container. But if you want to use Keras only and not TensorFlow, you have to build a custom container. Okay, so I mean, I guess it's gonna come, but for now you have to use my way. Okay, next question. What are the differences of running the containers in Fargate versus SageMaker? So what SageMaker really brings is the scaling, right? It's gonna, especially when you do distributed training, and distributed training with Keras is not easy to achieve. But if you use, let's say, MXNet or TensorFlow, and you use those built-in containers, then SageMaker takes care of everything automatically. So you just literally use an object in the SageMaker SDK called TensorFlow or MXNet. The script that you pass is your script becomes a parameter that you pass to this object, and it takes care of everything automatically. So you don't have to set up anything. So if you enjoy setting up distributed training in TensorFlow or MXNet yourself, yeah, sure, you could run on Fargate on ECS if you wanted. But you know, I'm lazy, and I find that the SageMaker SDK and the SageMaker managed infrastructure make it much easier, and I can just run anything that I want on demand at any scale, and I never have to set up anything when it comes to infrastructure. All right. Okay. So yeah, there are questions about the cost. So the cost of SageMaker is the cost of the notebook instance. If you use one, you don't have to. You could use the SageMaker SDK directly from your laptop, and that works as well, of course. So the notebook instance, it's like EC2. You pay per second depending on the type of notebook instance that you use. Then of course you pay for the training time per second, and again depending on the instance type that you use. But the really cool thing here is that SageMaker starts and terminates those instances automatically. So you will never overpay for training, which is a typical problem that a lot of customers have. They create infrastructure for training and they leave it on whenever, even if they don't need it, right? And that's that's a shame, because you're paying for machines that you don't really use. So here that's never going to happen, because SageMaker terminates the training instances automatically. And then when you deploy to instances, again, you pay per second per instance type. So this is mostly how you get charged for SageMaker. So demo like this, it's literally going to cost me 2 minutes of P3 8XL, which is, I guess, that instance is probably a few dollars per hour. I can't count, so I'll let you count how much that costs. But anyway, this is overkill for this kind of data set, and you could get away with using C4 or very small instances for that. But I'll refer you to the SageMaker pricing page. That's where you'll find all the information. All right, let me scroll back a little more. Not sure how much time we have left, so please feel free to shut me down when you need to. All right. Yeah, so there's a question here that's something that I didn't cover today, because we had to stop at some point. But I showed you how to train. Now the next step, possibly on SageMaker, would be deploying, of course. Okay, So you'll find some examples again in the sample notebooks in the SageMaker collection. You could build a custom container to serve those predictions. It would be quite similar. The only thing that you need to do is have a simple web server set up inside the container. This is how the TensorFlow and the MXNet containers that we provide do it. You have an Nginx web server in there, creating just with a little bit of Python code, just creating the endpoint. I think it's a Flask app actually, and just loading the model and serving predictions. But that's just one way of doing it. You could look, these containers are open source anyway, the TensorFlow and the MXNet container and so on are open source. So you could look at that and reuse that if you wanted, or you could do it any other way. Some people will have the same container to train and predict. Why not? You just need to account for the fact that in some cases SageMaker will call them for training and will call them for predicting. So if you use the same script for everything, there's a mode that SageMaker passes as well to let you know, hey, I'm training or predicting. Look at the TensorFlow examples in the SageMaker notebooks will show you how to do that. Or you could have different scripts to train and predict. But pretty much what it means is loading the model that you train, loading it from S3, and serving predictions using your favorite library interfaced with a simple web app. Okay, so not a lot of difficulty. Again, please look at the SageMaker examples on GitHub, and you'll find out. Okay. All right, it's time. So thank you very much for listening. I hope this was useful. It was definitely fun for me to do it. And if you have questions later on, if you need to get in touch, I guess the easiest way is just to ping me on Twitter and ask me your questions, share your project, and go and build cool stuff. All right. Thank you very much to the colleagues that helped me set this up, moderating and organizing everything. Great work, guys. And thank you very much for listening. So I hope to talk to you soon, right? See you on the road, probably. Bye-bye.